All right, I'm not sure if I assigned number 33 last time, so if you did not do it, go ahead and do that now. It's a relationship between attractive forces and vapor pressure. Go ahead and pause the video now. So what we're looking at here is a difference between those two substances listed and which one has a higher vapor pressure. Substances that have weak attractive forces will have high vapor pressures because they evaporate more readily. So between C2H6 and C2Cl6, the C2H6 has dispersion forces. So does the C2Cl6, except the C2Cl6 is made of larger atoms, a larger electron cloud, stronger dispersion forces. So for letter A, C2H6 will have the higher vapor pressure. Letter B, if you draw those Lewis structures, we see that F2CO experiences dipole-dipole forces. It's a polar molecule, whereas CH3OH experiences hydrogen bonding. Hydrogen bonding is stronger than dipole-dipole forces, so the F2CO will have a higher vapor pressure. Helium versus hydrogen. Both helium and hydrogen have 2 electrons total. And so in this case, what we're looking at is the size of the atoms or molecule. Again, both experience just dispersion forces. I suppose because the hydrogen molecule is made of 2 atoms, its electron cloud will be slightly larger than that of helium. And because of that, hydrogen has stronger dispersion forces, so helium will have the higher vapor pressure. A little bit about it last time. We said that the boiling point of a substance is related to its vapor pressure, or boiling in general is related to vapor pressure. So definition of boiling: boiling occurs when the vapor pressure of a liquid equals the pressure being applied to the surface of that liquid. Usually we're talking about atmospheric pressure. So a liquid will boil when its vapor pressure, the pressure exerted by its vapor, is equal to the atmospheric pressure or pressure pushing down on that liquid. Now keep in mind that the boiling point of a substance, if nothing changes, is constant. The temperature of a boiling liquid never rises above its boiling point. Nevertheless, the boiling point of a liquid will increase when the pressure on the surface of the liquid is increased or is greater. So again, telling us that the higher the pressure pushing down on the liquid, the hotter that liquid must get in order for its vapor pressure to equal atmospheric pressure. Remember, vapor pressure is directly related to temperature. So in order to increase the vapor pressure of a liquid, you need to increase its temperature. The other factor that affects the boiling point of a liquid is the strength of the intermolecular forces. So boiling point of a liquid will increase when its intermolecular forces are stronger. So substances with stronger attractive forces will have higher boiling points. Now, I asked this before, what is the boiling point of water? Some of you may have said 100 degrees Celsius. We just saw in letter A that that's not necessarily true. And so 100 degrees Celsius happens to be what's called the normal boiling point of water. Normal boiling point refers to the boiling temperature when the pressure is standard pressure. Pressure at sea level, about 1 atmosphere or 760 torr. So at sea level, water boils at 100 degrees Celsius. So let's look at some examples of heat transfer involving liquids. First, vocabulary terms: specific heat capacity, or sometimes just called specific heat. We've talked about this before. We've used this. Here it is again. The amount of energy needed to raise the temperature of 1 gram of a substance by 1 degree Celsius. I guess we could also say the amount of energy released when a substance cools, when 1 gram of a substance cools by 1 degree Celsius. So heating is endothermic, cooling is exothermic. So units for specific heat are, of course, joules per gram degree Celsius. So we use specific heat anytime a substance is undergoing a change in temperature. So if we want to know, for example, how much energy is absorbed by a substance when it heats up, we could use a specific heat along with Q equals MCAT. So what if a substance is undergoing a phase change and not a temperature change? So remember, a temperature change involves a change in kinetic energy. When a substance undergoes a phase change, there is no change in kinetic energy, so we can't use Q equals MCAT. So for any changes in state of matter or phase changes, we can use heat of vaporization, or as we'll see later on, heat of fusion. So enthalpy is just a fancy word. I usually just call it heat of, so molar heat of vaporization. This is the amount of energy needed to vaporize 1 mole of a liquid. Now keep in mind, we use heat of vaporization for liquid gas phase changes. So changing from a liquid to a gas, aka boiling, or changing from a gas to a liquid, that is condensation. So if a substance is boiling, a liquid boils, or a gas condenses, we can use the molar heat of vaporization in order to determine the amount of energy involved in the process. Now, heat of vaporization is a constant for a substance. So every substance has its own value. There's some values in the back of the book, Appendix E on page A12. Units, there's a couple different units for heat of vaporization. Now, technically, molar heat of vaporization, that's the energy in kilojoules per mole of substance that is either vaporizing or condensing. Sometimes, though, we'll be given heat of vaporization in joules per gram, the amount of energy in joules required to, say, boil a gram of a substance. So either way, either kilojoules per mole or joules per gram. So let's take a look at the example on page 462. All right, go ahead and read along with me, please. Calculate the amount of heat or energy in joules required to convert 180 grams of water at 10 degrees Celsius to steam at 105 degrees Celsius. So let's think about this for a second. We have water at 10 degrees Celsius, which is a liquid, and we want to turn it into steam, gas, at 105 degrees Celsius. So this actually, we can separate this into 3 separate steps or 3 calculations. And then ultimately, we're going to add those up. So we have both temperature change and phase change in this calculation. So let's go in order of what happens to the substance. If you don't, you might end up using the wrong constant. So first thing that must happen to that water is it must heat up from 10 degrees Celsius to, well, if it's a liquid, it can only get as hot as 100 degrees Celsius. We'll assume 1 atmosphere of pressure here. So how do we calculate the energy required to heat the 180 grams of water from 10 degrees Celsius to 100 degrees Celsius? We're going to use Q equals MCAP. So if you look in the solution, that's exactly what's done. So that's part of the process requires 6.77 times 10 to the 4th joules. Once all of the water has been heated up to 100 degrees Celsius, which happens to be the normal boiling point of water, the liquid will boil. So how do we calculate the energy needed to boil that 100 grams of water? We're going to use the heat of vaporization. So heat of vaporization of water, there's a table on page 462, has some other substances there as well. Either 2,260 joules per gram or 40.7 kilojoules per mole. We're given the amount of water in grams. We could convert that to moles and then use the molar heat of vaporization. But the book chose to leave the amount of water in grams. Take that, multiply it by the heat of vaporization, and for that part you get 4.07 times 10 to the 5th joules. And then once all the liquid has boiled to steam, it's still at 100 degrees Celsius. That steam will heat up to 105, an increase in 5 degrees Celsius. Notice something different this time. Take a look in the solution in step number 3. The heat capacity, specific heat capacity or specific heat of steam is different than the specific heat of liquid water. So in fact, the specific heat of ice is different than those two as well. So make sure you know what kind of water, what form the water is that is heating up, whether it's a solid, a liquid, or a gas. Here we have steam heating up, so we're going to use 2.03 joules per gram degree Celsius for the specific heat. And then ultimately, like I said, we're going to add up all of those values. Notice they're all in joules. Add them up, and you'll get the total amount of energy required to go from water at 10 degrees Celsius to steam at 105 degrees Celsius. All right, so opportunity for you to try this out on your own, practice it. Number 51 on page 494. Again, this is an example of a process that requires, or that involves rather, more than one change. We have a temperature change and a phase change. So calculate the total amount of energy required. Any constants that you may need will be in the back of the book. So go ahead and pause the video now and work on that. So first thing that needs to happen is the mercury needs to heat up from 25 degrees Celsius to its boiling point. So in that table, one of the tables, the boiling point of liquid mercury is given as 357 degrees Celsius. So just to heat it up takes, rounded to 3 sig figs, 7,790 joules. So if you want to just deal with sig figs at the very end, that's fine too, but I rounded each step. Next, after the mercury heats up to its boiling point, it needs to boil. So we're going to use the heat of vaporization. Be careful, don't use the heat of fusion. That's a different constant. So 292 joules per gram. And we get for that part to boil completely to gas. The mercury is 49,600, again, 3 sig figs, joules. Add that up, we get 57,390 joules. If you want, again, if you wanted to convert to kilojoules first, each of those would have 3 sig figs, and then if you added them up, we'd get 57.4 kilojoules. Or if you left it as 57,390 joules and then divided by 1,000 to convert to kilojoules, you get 57.390 kilojoules. Either way is fine. So again, lesson here, make sure you use the right constants, make sure you go in order of what is happening to the substance. Look at example 1313. Interesting. It talks about the amount of energy removed by sweating versus the amount of energy removed by drinking water and heating up water. So if you look at the solution, in order to heat up the ice water from 0 to 37 degrees Celsius requires 61.9 kilojoules. And to get rid of 400 milliliters of water through your body from sweating, 964 kilojoules. So what's better to cool down? Drinking a whole bunch of ice water or sweating? Well, sweating is, as it says in the book there, nearly 16 times more effective at removing heat than drinking ice water. In fact, drinking ice water is not a very good way to cool down, because when you drink that water, it needs to warm up the water. The water will warm inside your body, and that requires energy. So you're actually losing energy by drinking cold water. Ask my son, he knows all about that. He does not drink ice water when he is playing his games. Guess his chemistry dad should not have told them that. All right, so number 53 on page 494, similar to the last problem we just did. This involves water going through lots of different temperature changes and a phase change. So go ahead and pause the video and work on that now. I apologize, I misspoke. This is not the problem I was thinking of. In this one, you're mixing water of different temperatures and we're trying to find the final temperature. Let's do this one in class together. This one involves the transfer of energy from one sample to another. We can assume that the transfer is complete, and so there's quite a bit of stuff going on. Hopefully you didn't do that one yet. If so, we'll go over it in class. Apologies for that. All right, next up we have the solid state, some vocabulary terms. Temperature, the temperature where solid turns into a liquid. Remember, the process of a solid turning into a liquid is called melting. The temperature at which this is called, or the temperature at which this occurs, is called the melting point. The temperature where a liquid turns into a solid, recall that the process of a liquid turning into a solid is called freezing. The temperature at which this occurs is called the freezing point. What is the melting point of ice? Well, sort of a trick question. So let's go with what is the normal melting point of ice? At what temperature does ice melt? That would be 0 degrees Celsius. What is the freezing point? Okay, we'll go normal freezing point because I know some of you are like, I don't know. What is the normal freezing point of water? At what temperature does water freeze? So same temperature, right? So freezing and melting point are the same temperature, or occur at the same temperature. So of course, normal freezing point, normal melting point temperature that these processes occur when at standard pressure or 760 torr or 1 atmosphere of pressure. All right, so let's look at some heating curves and cooling curves. So heating curve shows endothermic processes. It shows what happens to a substance if you add energy at a constant rate. So let's go ahead and set up our axes. On the y-axis is temperature, and we'll just put in degrees Celsius. And then on the x-axis, it's time. So again, what we're going to do is we're going to show what happens to the temperature of a substance as you add energy at a constant rate. So let's start, let's say this is the melting point. So let's start down here for a substance. And let's say this is the boiling point. So if that happened to be water, melting point 0 degrees Celsius, boiling point 100 degrees Celsius. So if you add energy to a substance below its melting point, first of all, what state of matter is a substance below its melting point? It would be a solid. So if you add energy to a solid that's at a temperature below its melting point, what happens to that solid? It does not melt. It's got to heat up first. So it's going to heat up to its melting point. If you continue to add energy, what's going to happen to that substance? Well, it's not going to continue to heat up. In fact, its temperature at the melting point is going to remain constant. So notice that when a substance undergoes a phase change, its temperature does not change. So at this point, whatever time this is right here, the substance has been completely melted. It's liquid. And so if you add energy, that liquid is going to heat up, not forever, but it's going to heat up to its boiling point. Once the liquid reaches its boiling point, if you add energy, it is not going to continue to heat up. So again, we see phase change and no temperature change. At this point here, all the substance has been vaporized. It's all a gas. Continue to add energy. Temperature is going to continue to increase for quite a while. So notice something here. Look at the time it takes for the substance to melt. So this is melting. Versus the time it takes for the substance to boil. So this is boiling between here and here. It takes a lot longer. It takes more time to boil a liquid than it does to melt a solid. Or if we're adding energy at a constant rate, that must mean it takes more energy to boil a liquid than it does to melt a solid. By the way, on the graph, anywhere where there's a slope, that involves a change in temperature. We could use Q equals MCAT to calculate the energy associated with that temperature change. All right, let's take a look at a cooling curve. On a cooling curve, kind of the same thing. This time, everything on that graph is an exothermic process. Let's set up our axes. So we have temperature again over here, time here. Let's see if I left room for, call it freezing point this time, and boiling point. This time, let's start here. So this time what we're going to do is show what happens to the temperature of a substance if you remove energy at a constant rate. So suppose you start off with a substance that's at a temperature above its boiling point. First of all, what state of matter is it? It would be a gas. So if you remove energy from a gas that's at a temperature above its boiling point, what is going to happen? It is not going to condense yet. It's going to cool down to its boiling point. So now we have a gas at its boiling point. If you remove energy from that gas at its boiling point, it does not continue to cool down, but rather that gas will condense. It'll turn into a liquid. So right here we have all liquid form of that substance. If you remove energy from a liquid at its boiling point, it's going to cool down. Let's go a little bit more, I guess it looks like. Cool down to its freezing point. If you remove energy from a liquid that's at its freezing point, it will freeze. While it's freezing, its temperature remains constant. So right here at this time, we have all solid. If you remove energy from a solid, its temperature will decrease. So again, here we have condensing, and here we have freezing. So notice it takes a lot longer to condense a gas than it does to freeze a liquid. I guess that must mean that condensing is more exothermic than freezing. I will see that in just a second. So there is a cooling curve. All right, so how about calculations involving solids? Either change in temperature of a solid or change in phase involving a solid. First of all, when a solid undergoes a phase change, so let's say a solid turns into a liquid, that process is called melting. How do you calculate the energy required to melt a solid? It's not in the notes, I'm not sure why, but you're going to use a constant known as heat of fusion. By the way, the symbol for heat of fusion is delta H FUS. You may have saw in the table in the back of the book. Symbol for heat of vaporization, delta H VAP. So again, just like heat of vaporization, heat of fusion is a constant used for any solid liquid phase changes. So solid to liquid, melting, endothermic. Liquid to solid, that's freezing, that's exothermic. Again, either of those processes occurring, you'd use the heat of fusion for that substance. Take a look at example 13.7 at the top of page 468. Calculate the amount of heat that must be absorbed by 50 grams of ice at negative 12 degrees Celsius to convert it to water, liquid water that is, at 20 degrees Celsius. So going back to our heating curve, if this is the heating curve for water, we're starting right here, below the melting point, so negative 12 degrees Celsius. So that ice has got to heat up first. So it's got to go from here to here. So that would require Q equals MCAT, this time using the specific heat of ice, which you can see in the book is 2.09 joules per gram degree Celsius. That's step one in the solution. And then once the ice heats up to 0, it's going to melt. To calculate the energy required to melt the ice, we're going to use the heat of fusion of water, which is 334 joules per gram or 6.02 kilojoules per mole. So again, either one is fine. If you have a mass of water in grams, you can use the heat of fusion in joules per gram. If you want only given the molar heat of fusion, then may want to convert that grams to moles first. So your book actually has a value 6.02 or 334 depending on the units. And then once all of the water has melted, it's going to heat up from 0 to 20. That will require, again, Q equals MCAT, this time using the specific heat of liquid water, 4.18 joules per gram degree Celsius. Again, add all that up to get the total amount of energy required. And we see it is 22.1 kilojoules of energy required. All right, that concludes this lesson. We'll continue next time with phase diagrams. Thanks for watching.